As aircraft approached higher speeds, pilots reported sudden loss of control, unexplained buffeting, and structural stress that appeared without warning. Engines were blamed. Pilots were blamed. Airframes were reinforced blindly. The real problem was that engineers could not see what air was doing at high speed. John H. Stack solved this by creating test systems that made airflow visible and measurable before aircraft ever flew. His work turned unknown aerodynamic forces into data, and that changed aviation before the war even reached its peak. John H. Stack was born on March 6, 1906, in the United States. He grew up during a period when aviation was still in its infancy, and aeronautical engineering barely existed as a formal discipline. Early aircraft design relied heavily on trial and error. Engineers built prototypes, tested them in flight, observed failures, and modified designs afterward. This process was slow, expensive, and dangerous. Many problems were only discovered after aircraft were already airborne. Stack pursued engineering education at a time when aerodynamics was transitioning from experimentation to science. He studied mechanical and aeronautical engineering, with a focus on airflow behavior and structural response. His training emphasized measurement, testing, and validation rather than theoretical speculation. This approach would define his career. After completing his studies, Stack joined the National Advisory Committee for Aeronautics, NACA, the organization responsible for advancing American aeronautical research. NACA was not an aircraft manufacturer. It did not design fighters or bombers. Its role was to solve fundamental engineering problems that industry could not address alone. Stack entered NACA as a young engineer, tasked with studying airflow at higher speeds than had previously been explored. By the early 1930s, aircraft performance was increasing rapidly. Engines produced more power, airframes became stronger, and aircraft speeds approached regions where existing aerodynamic models began to fail. Pilots reported instability, control reversal, severe vibration, and structural stress that could not be predicted by existing wind tunnel data. The problem was not isolated to one aircraft or manufacturer, it was systemic. The limitation came from testing capability. Conventional wind tunnels could not reproduce the airflow conditions experienced by aircraft at high speed. Air behaved differently as velocity increased, especially as compressibility effects became significant. Shock waves, pressure changes, and control surface interactions appeared suddenly and unpredictably. Engineers were effectively blind to these phenomena until aircraft encountered them in flight. Stack recognized that aviation could not advance safely under these conditions. Increasing speed without understanding airflow behavior meant accepting unpredictable failure. Reinforcing structures or limiting performance was not a solution. The core problem was the lack of reliable data at high-speed conditions. At NACA's Langley Memorial Aeronautical Laboratory, Stack became a central figure in addressing this challenge. He focused on the development of high-speed wind tunnels capable of simulating airflow closer to real flight conditions. This was not a matter of scaling existing facilities. New testing systems had to control air density, pressure, and velocity precisely. Instrumentation had to measure forces that had never been recorded accurately before. Stack led efforts to design and operate pressurized wind tunnels that could achieve higher effective airspeeds without requiring extreme physical velocity. By increasing air density through pressurization, these tunnels could reproduce compressibility effects at lower speeds. This allowed engineers to observe shock formation, control surface behavior, and pressure distribution under conditions similar to those encountered in high-speed flight. These facilities transformed aerodynamic research. Problems that had previously appeared without warning during flight testing could now be identified in controlled laboratory conditions. Engineers could measure where airflow separated, where control surfaces lost effectiveness, and how pressure changes affected stability. Designs could be modified before aircraft were built or flown. As Europe moved toward war in the late 1930s, the importance of this work increased dramatically. Military aircraft needed to fly faster, climb higher, and operate safely under combat stress. Losing aircraft to unknown aerodynamic effects during testing or early deployment was no longer acceptable. Stack's wind tunnel systems provided the US aviation industry with a decisive advantage: predictability. Unlike aircraft designers, Stack did not create a single iconic airplane. His contribution existed inside the development process itself. Aircraft manufacturers relied on NACA data generated under his direction to shape wings, fuselages, and control systems. These insights influenced multiple aircraft programs simultaneously, multiplying their impact. When World War II began, American aircraft entered service with a level of aerodynamic understanding that had not existed a decade earlier. Designers knew where limits existed and how close they could approach them safely. High-speed dives, control response, and structural margins were no longer based on guesswork. They were based on measured data. Stack's role during the war expanded as demand for rapid development increased. Aircraft programs moved faster, and mistakes became more costly. His testing systems allowed engineers to validate designs before production, reducing failure rates and accelerating deployment. This contribution did not appear in combat reports, but it shaped every aircraft that relied on controlled high-speed performance. By the end of World War II, the foundation for modern high-speed aerodynamics had been established. The ability to test and understand airflow near critical speed regimes did not end with the war. It became the basis for post-war jet development and later supersonic research. Stack's work ensured that speed became an engineering variable rather than an unknown threat. John H. Stack did not influence World War II by flying aircraft or commanding forces. He influenced it by removing uncertainty from aviation design. By building systems that made airflow measurable before flight, he allowed engineers to solve problems on the ground, instead of losing aircraft in the air. This quiet transformation defined how modern aviation would be built before combat ever began. When the United States entered World War II, American aviation faced a unique challenge. Aircraft development could no longer follow a slow cycle of prototype, failure, and redesign. Combat demanded immediate reliability. Fighters, bombers, and transport aircraft had to perform as expected from the first operational deployment. Any hidden aerodynamic flaw now translated into lost aircraft, delayed production, and reduced combat effectiveness. The work led by John H. Stack at NACA directly addressed this pressure. His high-speed and pressurized wind tunnel systems allowed engineers to test aircraft components under conditions that closely matched combat flight. Wings, control surfaces, and fuselage shapes were evaluated at speeds where compressibility effects appeared. Designers no longer had to wait for dangerous flight tests to discover instability or control loss. One of the most critical problems solved through Stack's testing systems was high-speed instability. As aircraft dove at higher speeds, pilots reported sudden pitch changes, control stiffening, and vibration that could lead to loss of control. These effects were poorly understood before the war. Stack's facilities made it possible to observe how airflow behaved around wings and tail surfaces during high-speed flight and dives. Engineers could identify dangerous pressure shifts and modify designs before production. Fighter aircraft benefited immediately from this capability. Designs such as the P-47 Thunderbolt, P-51 Mustang, and later high-speed variants relied on NACA data to refine wing profiles, tail sizing, and control effectiveness. These aircraft were expected to dive rapidly, recover safely, and remain controllable under combat stress. Stack's wind tunnel data reduced the risk of catastrophic behavior during these maneuvers. Bombers faced similar challenges. Large aircraft operating at high altitude encountered compressibility effects that affected stability and control. Long wings, and heavy loads increased sensitivity to airflow changes. Through controlled testing, engineers could adjust wing thickness, aspect ratio, and control surface balance. This reduced unexpected structural stress and improved handling during high-speed descent and evasive action. Stack systems also influenced how rapidly aircraft could be developed and deployed. Wartime production schedules left little margin for redesign after fielding. By identifying aerodynamic limits early, NACA testing reduced costly delays. Manufacturers could move designs into mass production with greater confidence that aircraft would perform safely within expected envelopes. Another important contribution was standardization of data. Stack's work ensured that aerodynamic behavior was measured consistently across different programs. This allowed lessons learned from one aircraft to be applied to others. The result was not a single breakthrough aircraft, but an overall increase in reliability across the US aviation fleet. The strategic value of this work became apparent as the war progressed. Aircraft losses due to unknown aerodynamic behavior declined. Pilots reported fewer unexplained control issues during high-speed flight. Training became more effective because aircraft behaved predictably across a wider range of conditions. These improvements were incremental but cumulative, affecting thousands of sorties. Unlike combat innovations that produced immediate tactical advantages, Stack's contribution operated at the system level. His work did not change how aircraft were flown in battle. It changed how aircraft were designed before they ever reached the front lines. This distinction is critical. Reliable performance was engineered into the aircraft rather than compensated for by pilot skill alone. As the war accelerated development cycles, Stack's facilities became increasingly essential. New aircraft variants could be evaluated quickly without exposing pilots to unknown risks. Engineers could push performance limits methodically instead of blindly. This capability allowed American aviation to increase speed and altitude without sacrificing safety. By the later years of World War II, high-speed aerodynamic testing was no longer optional. It had become a foundational requirement for aircraft design. The systems John H. Stack built ensured that American aircraft entered combat with known limits and controlled behavior. This predictability reduced failure, preserved pilots, and sustained operational tempo. John H. Stack did not contribute to World War II by producing weapons or commanding forces. He contributed by ensuring that aircraft behaved as expected when pushed to their limits. In a war where speed and reliability mattered more each year, his work turned uncertainty into data and data into survivability. The end of World War II did not reduce the importance of the systems John H. Stack had built. On the contrary, the transition to the post-war era made them even more critical. Aviation did not slow down after 1945. It accelerated. Aircraft entered speed regimes that magnified every aerodynamic uncertainty Stack had worked to eliminate. As piston engine aircraft reached their practical limits, designers moved toward jet propulsion. Jet aircraft operated at higher speeds, encountered stronger compressibility effects, and experienced new forms of instability. Without reliable ground-based testing, these aircraft would have faced the same dangerous cycle of flight failure that had limited earlier aviation. Stack's wind tunnel systems provided the foundation needed to explore these regimes safely. At NACA, Stack continued to lead the development of testing facilities capable of simulating transonic and near supersonic conditions. New tunnels expanded pressure control, airflow, uniformity, and instrumentation precision. Engineers could now study shock formation, boundary layer behavior, and control effectiveness as aircraft approached the sound barrier. These were not academic studies. They directly informed aircraft design choices. The knowledge generated through these systems influenced the first generation of American jet fighters and bombers. Aircraft such as the F-86 Sabre and early jet bombers relied on aerodynamic data that traced directly back to the testing methods Stack helped establish. The ability to predict control behavior near critical speed ranges became essential as flight envelopes expanded. Stack's influence also extended into structural and systems engineering. Aerodynamic loads measured in wind tunnels informed material selection, reinforcement strategies, and control system design. Aircraft were no longer overbuilt blindly or underdesigned unknowingly. Structural margins became calculated rather than guessed. This reduced weight, penalties while maintaining safety. Beyond military aviation, Stack's work shaped how aerospace engineering was practiced. The principle that flight behavior must be understood before flight became standard. Wind tunnel testing, computational validation, and incremental envelope expansion replaced intuition-driven design. This methodology became embedded in both government research and private industry. When NACA transitioned into NASA in 1958, the research culture Stack had helped build remained intact. High-speed aerodynamics, transonic testing, and data-driven design became central to space and aerospace programs. Space vehicles, re-entry bodies, and high-speed aircraft all relied on controlled testing environments derived from Stack's original concepts. What distinguishes Stack's legacy is that it did not produce a single visible invention. There is no aircraft bearing his name. Instead, his contribution exists inside the process by which aircraft are designed. Every modern high-speed vehicle depends on the ability to predict airflow behavior before flight. That capability did not exist before his work. Stack did not eliminate risk from aviation. He made risk measurable and manageable. This distinction allowed engineers to push boundaries without blind failure. As speed increased and missions became more demanding, systems based on Stack's methods prevented aviation from collapsing under its own complexity. In historical accounts of World War II, engineers like John H. Stack rarely receive attention because their work did not appear on the battlefield. Yet their impact was decisive. Aircraft that entered combat with predictable behavior preserved pilots, reduced losses, and sustained operational momentum. These outcomes were determined long before missions were flown. John H. Stack helped transform speed from a liability into a controlled variable. By building systems that revealed how air behaved at high velocity, he ensured that aviation could advance without self-destruction. This contribution shaped World War II and defined the future of flight, not through spectacle, but through engineering discipline embedded deep within the design process.